All right, so now I'm going to start in on vector-valued functions. Okay, and I'm going to start by talking about what did we learn in Cal BC? What do we already know about vector-valued functions? How can I extend that a little bit? Next time we'll talk more about space curves and let's see. Yeah, we're going to let this kind of break out into three-dimensional space. I think for now I'm going to be talking about just plane curves. Okay, so what do we know from Cal BC? Okay, and if you are just now, if this is new to you, I'm going to tell you it shouldn't be that much of a surprise. So what we know is that from calculus is that we start talking about parametric equations, you know, the function f of t is not really how we would write it. Actually, I think we would occasionally write it like this in AP calculus. I can never remember until I get in and actually go to do it. But it's kind of like, you know, it's going to have a vector. It's going to have two different functions of t. It could be like cosine of t, e to the t. That would, well, I'm not sure what the graph of that would look like. I think that y is going to keep increasing and x is going to go back and forth, so I think it's going to go like that. And I think that the waves would get more spaced out because e to the t grows fast. But that's, you know, not super important to us. You know, has a graph that could look like, you know, maybe. And moreover, the way that we write this is going to induce an orientation. And that is something I talked about briefly in the course last year. It wasn't a huge deal. So I'll just say, you know, since I already put that arrow going there, that the way that we have set this up, you know, say it orients it like that. You can reparameterize to change the orientation, and then other things will happen, and we'll talk about that when that happens. Okay, what else do we find out? We found out how to find the slope. Okay, dy dx for a parametric curve was dy dt divided by dx dt, or y prime of t divided by x prime. It was great. Well, here we are. We're back in calculus, so yeah. Dy dt over dx dt. Provided that dx dt is not 0. Now, if dx dt was 0 and dy dt was non-zero, that would be evidence that we had something like this, like a vertical tangent. If they're both 0, more analysis is necessary. That could be where you have you know, sharp corner or something like that. You could have, I don't remember how it goes. I just know that more analysis is necessary when you have both dx dt and dy dt simultaneously 0. Okay, and then we'll talk about that. That's I know that's a topic on the quiz next time. So, what else do we know? Okay, we also found out how to find the second derivative, which for our purposes in AP Calculus really only tell you about concave up or concave down, right? But we learned that you find this by taking the derivative of dy dx with respect to t, right? Because dy dx is going to be a function of t. It's going to be a fraction usually, unless x prime is a number. You take the derivative of dy dx, and then this is pretty obscure. You may have forgotten about this, but then you divide by dx dt. And rather than going through in terms of like the quotient rule and explaining it to you why you divide by dx dt, I'm going to refer you to my YouTube channel. I've got a video that it was a question somebody asked last year, and I was like, I think I know why. I think it has to do with the quotient rule. I dove in and really, you know, pulled it out of what you're doing when you're taking the second derivative of y with respect to x both times. So I would just.
If you treat all those things as variables, which I know you're not supposed to, it will end up.
That is also true. That symbolically, yes, this feels right. That was another thing. That's generally what I do to kind of just in AP Calculus to convince people that like, okay, this is what you need to do. Like, hey, look, like symbolically it works, and then everyone's like, oh yeah, that's great. Except maybe maybe that's not quite exactly what you can do, but you know, it works. So. What else do we know? We found out how to take the length of that curve. And we did that by integrating between, make this smaller, between two time values, or two t values, we're going to integrate the square root of x prime of t squared plus y prime of t squared. And if you remember, we loved this in AP Calculus because, I mean, the odds of this actually being integrable are basically not existing. So this is always a calculator question or just like multiple choice, which one is the right integral. And we like those.
Left it there.
Yeah, we did. Or yes, right, but do not evaluate. Okay, that's not really been an option for me this year because of having to do everything in Schoology, but those are good problems too. And I'm missing a DT. Okay, and then something else. Okay, that I'm not even going to write down, but something that we did in AP Calculus was we could calculate a new position if all we were given was like a velocity vector and an initial condition. We could find the new position just by integrating x and y separately. Okay, and then that's still going to happen. What we're going to do is we might just integrate the vector, remembering that just hold on to all the pieces. In AP Calculus, we just did them all separately. So that was fun. Okay. What's going to be new to us today is going to be, say you've got a plane curve that does not self-intersect. I'd make sure they're, yes. If a smooth curve C given by x equals f of t and y equals g of t does not cross itself on an interval t between a and b, then we can, basically we're thinking about that. If we rotated this curve around the x-axis, okay, and so I believe that it's saying, yeah.
Making a form.
Yeah, exactly. So, you called it a form? I think that is actually what it's called. But it's just it's a surface. Okay, it's just in AP Calculus we take the whole region to make it solid, but you can imagine if you just had the shell, that would be a surface. Okay, and so what you got to do, and I think I might not make it have so much change in direction, might give it a little bit of wiggle, but I think I want it to be monotone increasing. This is going to be, I don't know, it's going to be a bell, isn't it? Yes, it is. So we rotate it, it becomes a bell. How we're going to find, okay, I'm going to try to, it'll work, yeah. Good, yeah, it'll work. No, that's not how it's supposed to go. I think it's maybe like that. I don't worry too much about it. Anyway, that's kind of my surface of revolution. And how we're going to find the area is we're going to add up these small little bands of area. Okay?
We didn't do that before.
Oh no.
No, we did not take the area of a surface of revolution.
We
What
had
did
to do
what
that
did
in
we do?
physics.
Yeah, it's not so bad though, because what you need to what you need to consider is this band, and we can break out this band.
What did we do before? Just the surface?
We did volumes,
Oh.
and
So what are we finding there?
we did perimeters also, but not after the rotation.
So how do you find the area of a 3D object? Is that not volume?
This is a two-dimensional object embedded in three-dimensional space, right? It's like my lecture notes, it is a three-dimensional object, but we kind of assume that it has no width.
It's not
Yes.
thick. It's just
No
a flat
thickness, yeah.
bell.
Yeah. So what I'm going to do is I'm going to take this thing and kind of look at it as, okay, one of these. All right. And so this is going to be 2 pi r, right? Where r is this height of the function. But if we were rotating like kind of a sideways curve around the y-axis, this would be a different consideration. So we're going to need to make sure that our r is the right component function over here, right? Okay, now but I'll talk to you more about it. And then this is going to be some kind of L, some kind of length. Now, if you go back up here and look at where L traces back to, it's a small piece of arc length. Okay, so really what we're going to do is we're going to say that surface area is going to be the integral of 2 pi RL. Okay? And
dy.
yeah, that's the question, right? And it's going to be dt because these things are, expressed in terms of t. But so I'm just making sure. Yeah.
I don't really
Okay,
understand how
so-
this is different. Like, is that the same equation as the volume?
No, the volume was equal to the integral of pi r squared because we were going to add up a bunch of areas to get the volume. Here we're going to actually add up a bunch of. You could think of them also as like circumferences.
Okay.
And then the thing that we're going to is going to be, you could call it LDT being the thing that you're add up on. But that's kind of a different discussion. So we're going to say that it's going to be the sum of 2 pi RL with respect to time, definitely. As but if we're going to restrict here, those are going to imply 2 time values. So from time 1 to time 2. Okay? And let's say that if, and then this kind of branches off into 2 cases. And I'm realizing I'm going to the edge of my shot. Yeah. Okay, if we're rotating around the x-axis like in my drawing, then r is going to be y of t. Right? Because the radius is just like the distance from the x-axis to the graph, which is the y value. And then if rotating around the y-axis, I'll just draw you a picture of that. Maybe it, something like that. That'll make something closer to a cone, I think. Maybe a volcano. I don't know. But anyway, if we rotate around the y-axis, then we'll have best effort. Ooh, that's rough. Anyway, if we do that, then maybe it'll look better if I do one of these. No, I think that made it look worse. But now it looks like a beaker. So in this case, the radius is going to be x of t. But either way, this little piece of arc length is going to be L is going to be the square root of dx dt squared plus dy dt squared. Okay, and in retrospect, I probably could have started with the idea of a Riemann sum and built that up, but that horse started out the barn. And I want to keep this video relatively short. So that's going to be something, and maybe I'll show you an example of how to actually do this. Maybe with one where the actual numbers would be super nice. I know just the one. Okay, go back over here. Things we already know them, so I don't need to see them anymore. I'm going to go consult with the textbook, and yeah, I'm not super into that example, but I had an idea. I was going to use. Y'all aren't going to love this one so much, but it'll be good for you. Let something like x equals maybe t minus 3. Maybe plus 3. Yes, that's what I want, because I want this to be like good and in the first quadrant. And then y is going to be, let's say, 3t minus 1. Okay. If x and y are both linear in t, then the graph will be a line. And I'm realizing I recorded a video about lines and planes in space. I didn't talk anything about lines, the equation of a line or the equation of a plane. I'll just start in next time with or maybe I'll just attack it if we need it. I know we'll need it eventually, but it'll be fine. Okay, yes, sir.
I think so. You have that bit.
Okay, so this is going to make a line in the plane, and let's say t is going to run from maybe I'll make that a +1 so that t can run from 0 to something else. Yeah, so we'll start at 1 or 3, 1, and then x and y are just both going to increase. So maybe I'll just let this go from 0 to 1. Okay, I can actually draw you a picture of this. It's going to start off at 3, 1, and it's going to have a slope of 3, and so it'll maybe look like that. So what's going to happen is that this is going to be, when I rotate it around the x-axis, this is going to be one of those things that, no, they still do, that the cheerleaders at A&M yell through. Yeah, you know what I mean? The big cone.
Sense.
Yeah, the cone, but that's cut off. That actually has, I think it's got a mathematical name. I just can't remember it. But I think of it as the cheerleader cone. Okay, so when I rotate this around the x-axis, let's say, it's going to make that cone, and the area we're going to rotate around the x-axis, and the area is going to be the integral of 2 pi RL dt. T is going to pretty clearly run from 0 to 1. Okay, so I'm going to factor out the 2 pi. R, since I'm rotating around the x-axis, is going to be y of t. Okay, so y of t is going to be 3t plus 1. And then L is going to be that square root. And the nice thing about this situation is dx dt is 1 plus dy dt is 3. So it's going to be 9 and 1 is 10. The square root of 10 is just a number, and that's one of the things we learned in calculus is that we can just factor out a number. So 2 square root of 10 pi integral from 0 to 1 of 3t plus 1 dt. And this is something we might like to work. So, and then that's probably the best advice I can give you is that in multivariable calculus, even more so than single variable calculus, all of the excitement or all the difficulty is in the setup of these problems. Usually if you get it set up right, the actual integration is not that bad. Okay? Especially when we go to do double and triple integration, the integrands, they shouldn't be too nasty. We won't be doing a whole bunch of trig substitution and UDV and then UDU or UDU and then UDV. No need for that. Okay. That's an example of a surface area of revolution. Let's see, based on my notes, that's pretty much all I've got for vector valued functions before we go and break out into space and look at tangent, normal, and binormal vectors, all that stuff. That'll be in the next video.
Will we be solving past that?
Oh, yeah. You'll be solving past that. I kind of just assumed that
You know how.
we were good on that, but why not, right? For some of us, it's been quite a while since we've integrated. So I'll just remind you about the 3-step process just as soon as I find my purple marker.
You threw both of them away.
No, not the second one. I did throw one away. All right, I'm back. I lost my marker in my jacket pocket. So, all right, what I'm going to do is I'm going to hold on to this. I'm going to get an antiderivative. Oh, man, 4t plus 1 would have been a much better choice, right? This is 3 halves t squared plus t as t runs from 0 to 1. That's pretty nice, too, because that's going to be 5 halves. Okay, so that's 2 pi square root of 10, 5 divided by 2. So I've got, I don't know, pi times the square root of 250 or something. I don't know, whatever. That's a safe place to stop. In this class, there's not really any hard, fast rule about 3 decimals and stuff. I think in general, we're going to prefer exact values. But, if you want to round to 3 decimals because that's what you're used to, no judgment. Ideally, though, we're not going to pull out a TI-84 to do that one. We're not going to need to. Because there will be plenty of situations where we need to pull out the TI-84 to run an integral. You should know if something's antidifferentiable, it might just be faster to run the integral by hand than to go and actually find your calculator and make that happen. So that's all I've got on this video. So I am actually ending now.